Da 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 da. I'm gonna be coding. This is cool. Oh, bro, so difficult. Fuck's sake. Why is it so difficult? Even the easy questions are like difficult. Fuck. I mean, it is a medium question, but oh, if I need code, love you, need code. What? Say what? What am I doing, bro? They should have been. Bro, why is everything so hard? Oh my god. 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 It is 2-pointer question. Let's see the solution. It's similar to what I was doing.
And actually, I pretty much never implement it.
Okay, I'm gonna look at the roadmap. I don't want to do binary search. I want to do a binary search. I want to look at some trees, and it's similar. I'm gonna look at some trees for my own sake. For my own sake, I wanna consult my thing here. So trees are like trees and tries are pretty useful. So I'm gonna learn trees and tries, and heaps is pretty important too. So we're gonna study the heaps, backtracking, the main thing, obviously, backtracking, graph, and BP isn't that intervals are kind of needed, and yeah. So right now this is the goal with my BSA. That's my fuck. Okay, we have trees, tries, backtracking, and graphs, heaps, and intervals. So that is the way that I'm gonna approach the next set of things. Linked list isn't that important for the yeah, I might do sliding window now and then. Sliding window concurrently, but trees is what I'm gonna do now today. I'm gonna take this.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a pretty easy and popular question: invert binary search tree. So all they tell us to do is invert a
It needs to be concurrent. I'm a real I'm a real one, you know. I don't want to do binary tree per se, but oh my god, like I just wanna cry myself to sleep. Shut the fuck up. Okay, what is the question? You're given a root. You're given the root of a binary tree. Invert the binary tree and return its roots. That's it.
is invert a binary tree. And what exactly does that mean? So let's say that this is our initial tree. To invert it is basically what you can tell in the output, right? So the root stayed the same, but you can see its two children, which were left child 2, right child 7, were swapped, right? So 7 is now on the other side, 2 has been moved, right? So basically we took these and then we swapped them. And when they say invert the binary tree, it's a recursive definition. So take a look at this subtree, right? You can see since we moved it to this side, that's where it is, right? But notice how even these subtrees are different now, right? 1 was initially on the left and 3 was initially on the right, but now 3 is on the left and 1 is on the right. The exact same thing happened with this tree, right? It was moved over here to the left side, but then its children were also swapped, right? So 9 was moved to the left, 6 to the right. So when they say invert the binary tree, what we're saying is visit every single node in the tree, right? And every time we visit a node, take a look at its 2 children and swap the positions of the children, right? So in other words, if we're given a tree, look at the root node and take its children and then swap the positions and then recursively run invert tree on the left subtree and run invert on the right subtree. So it's a recursive definition. So we can solve this problem with recursion. We can do a depth first search, whether it's pre-order or post-order, it doesn't actually matter. A depth first search will allow us to solve this problem recursively. So this problem would probably be a lot more annoying if it were iterative, but luckily we can do it recursively. So we can first check the base case. So if the root is null, then we can return null. We don't have to continue. Otherwise, what we're going to do is swap the children. So we're going to save the left value.
Let's talk about an important data structure known as binary trees. So let me draw a binary tree. It might look something like this, where we have different nodes here, and so a node is just like a circle with a value in it. We're drawing numbers in them, but they could store pretty much anything that you want. For any node that's in the tree, say this one here, well, it has at most 2 different children. If we call this the root here, then it has a root.left, which is basically a reference to its left child, and so its root.left is going to point over to here, and it also has a root.right. So root.right is going to point over to this guy here. So each node, basically in a programming language, it might look something like this. You would have it as a class. We'll call it a class node. And so it basically have 3 different things. It would have a root.value. So basically, what is the number it's storing? And so we'll say that one is equal to 1 here. It would have a root.left, which is going to be a reference to another node. So it's going to be a reference to another node, or it's going.
So let's say I have like a couple of jujitsu moves and I don't really want to invert it. Why do I want to invert it? Why do I want to invert my jujitsu moves? Yeah, some basic functions.
To be null. So for this guy here, its root.left is actually pointing to null, or in Python it's going to be none, saying that it doesn't have a root.left. And it also has a root.right. So it has a right pointer or reference to another node, or again, that could be null because this guy here, both his left and his right are null. Okay, there's lots of terminology here. So regarding the entire tree that you were given, this is the one and only root. So if this was your tree that you were given, this is the actual root. However, if you are to go over to root.left, which is going to be this guy, then you kind of have a different tree here. We're particularly talking about this subtree. So when you're talking about this subtree, well, then this guy is the root. So this guy would also be a root. So you kind of have some global root, which is among the whole tree you were given. This is the one and only root. But then if you're talking about any particular node in here, they are kind of a tree themselves. They're a subtree. Now trees have what we call leaves, and those are all of these guys. So these are what we call leaf nodes. They basically don't have any other branches, because you could picture this as a branch. You're basically from one part of the tree, you're taking yourself to a different part of the tree. These guys here are the leaf nodes, because from themselves they do exist, but they don't have a left and a right. So their left would be null and their right would be null as well. Now you might also hear the term parent. So here, if you're regarding some particular node, this could be a parent to its different children here. So this would be one of its children, and this would be another child over here. So if you're ever talking about a parent-child relationship, we mean the one that's above it, basically. So from the parent, you would go down to the children. Now what's kind of counterintuitive about the relationship is that notice that when I was drawing my class here, so if I had an object here, I had a root and it has a value, a root.val. It also has a root.left, so that's basically its left child. It has a root.right, but what we generally don't have, although you totally could, is the root.parent. This just doesn't exist in most implementations for who knows what reason. LeetCode decided that it's not going to be present, so generally this is the relationship we're given, which means more formally, it should be written like this, because as we'll see, trees are actually a subcategory of graphs. And so trees are actually what we call directed graphs. We have a direction. We have from here, you can get to over here, but from here, a child, you can't actually get over to your parent. Again, in some implementations, you could have that existing, but in LeetCode, generally this is the class you're going to be given. Okay, there's a little bit more terminology here, particularly this tree is actually a specific type of trees known as a complete tree, or sometimes called a full tree. And a complete tree means that this level is fully filled out, so is this one, and this one is mostly filled up from left to right here. So basically, we don't have this last piece here. If we did have this last piece, so this is some number here, well then this is actually what you call a perfect tree. So it means it's completely filled up here. We have the 3 levels. We have 1 thing here, 2 things here, 4 things here, and nothing is at the end. So that would be a perfect tree. What we have here is a complete, sometimes called a full tree, which means it's all the way filled up except possibly the end. We're missing something at the right side, and that's totally fine. And this would also be a complete tree as well. This would also be a complete tree. And so with this one, this is a complete tree and it's a perfect tree. But then if you have this here, this is not a perfect tree, but it is complete. Now, something that's kind of interesting about binary trees is that you can actually kind of think about them as an array. So let me kind of move this over here and draw its array representation. So this is the representation that kind of in memory, meaning that if you create objects that have a class, this is how it would look with like one thing pointing to another thing. But in theory, you could kind of have this as just an array, because if you had, and let me just leave the first position blank here, you'll see why in a moment. If you had this one as 1, then 2, then 3, then 4, then 5, then 10. Notice I'm just drawing it in order here. So given some index I, which is going to be 1 here, well then its left child is going to be located at 2 times I, and its right child will be located at 2 times I plus 1. So let's just test that out here. If I is equal to 1, we're saying that its left child would be at 2 times I, which is 2. So that's right, because the parent is 1, its left child is 2. We can see that over here. And for its right child here, we can see that it's going to be 2 times I, which is 2, plus 1. So that means its right child is over here, and it is, because for 1 is the parent and 3 is the right child. We have that relationship right there. And that is going to work for any position in the array. The only problem is that if you have something like 4, we would have 2 times I should be your left child, which is located at index 8, except that's outside the array. So if you go outside the array, that just means it's null, meaning we don't have any there. Now this also works if you don't have a complete tree. So if we had something like this tree here, well this is totally valid. It's just that it doesn't have a right over here. So we lost the 3 and the 10. Well then if we're talking about the 1, well then its right child should be at position 3, which is over here. And so if you have a blank here, or you could kind of mark this as say a -1, well that's just a way of saying that it's null, and that's totally correct. So binary trees have an array representation as well, and you'll often see this in LeetCode. LeetCode might actually tell you that this is kind of the input you're given, and it might look like an array, but if they're talking about
Binary tree. Binary tree.
trees, they're probably talking about a binary tree representation given in its array form. Now another important quality of binary trees is that they generally have a height, and so the height is basically just as well, and you'll often see this in just means it's null, meaning we don't have any there. Now this also works if you don't have a complete tree. So if we had something like this tree here, well this is totally valid. It's just that it doesn't have a right over here. So we lost the 3 and the 10. Well then if we're talking about the 1, well then its right child should be at position 3, which is over here. And so if you have a blank here, or you could kind of mark this as say a -1, well that's just a way of saying that it's null, and that's totally correct. So binary trees have an array representation as well, and you'll often see this this in LeetCode. LeetCode might actually tell you that this is kind of the input you're given, and it might look like an array, but if they're talking about trees, they're probably talking about a binary tree representation given in its array form. Now, another important quality of binary trees is that they generally have a height, and so the height is basically just the depth here. So including this node here, the root all the way down to the bottom, this would have a height of 3. And you might also see this called maximum depth. So basically this is depth level 1, 2, and 3. So it has a height or maximum depth of 3. Now subtrees also have a height as well, because if you're talking about kind of this guy as the root here, well then he is a tree. It's a subtree of this main tree, and so this tree would have a height as well. So this guy, he would have a height of 2 because he has himself and he also has going over here. And so that means we could kind of define a leaf node as something that has a height of 1 because it just has itself, it has nothing to the left and nothing to the right. And just to be super clear about the height here, if the tree actually looked like this, well, we wouldn't go down to the right side because that is nothing. It's going to be basically the maximum of going from the top to the bottom. So we would ignore that there's nothing to the right, go from the top to the bottom, and we would see this still here has a height of 3. Now in practice, we're generally concerned with some sort of traversal on the tree. So for example, you could do what's called a depth first search, or basically a depth first traversal, where you're going to start at the root because that's what you have access to, and we prioritize depth, which goes this way. So if you go over to 2, the next thing we're going to see is not 3. In a depth first search, we're prioritizing depth, so we're going to keep going down all the way. And generally how and then 4. And then after we see the 4, well, we're still going to try and go left here, except that's null, so that's nothing. So we'd kind of quickly come back up here and see, okay, after we've seen the 4, well, then we're going to go right. Okay, there's nothing there. Now we're done with the 4. We've visited both itself and its left and its right. We're done with that, and so we're at the 2. Now we need to see its right side, which is going to be the 5. So we see the 5. Okay, cool. We see its left, which is nothing. Its right, which is nothing. We come back up here, and then we're done with the 2. So we come back up here. With the 1, we still haven't visited its right side, so we will see the 3 next, and then we are going to see the 10. So that is going to be the order of our traversal. This would kind of return back up here, return back up here, and then we'd be done our search. Now for depth first search, there's basically 3 different ones that you might do, and they're all very similar, but just a slightly different order of processing. So there's going to be pre-order traversal, there's also in-order traversal, and there's also called post-order traversal. And what this means is basically the order in which you process the node itself and its left and its right. Pre-order traversal basically means that you first consider the node you're currently looking at. So if you're looking at this guy here, it means you process it, which just think about printing. So basically you'd print the value of 1. So we process the node itself first, then you process its left thing, and then you process its right side. Okay, so you first do the node, then the left, then the right. We actually just did a pre-order traversal. So we'd visit the root, and we immediately process that because we process our current node first. By process, we just mean print the value, so 1. Then we go over to the left side, and so we see 2. Okay, we do that. We print 2. We go over to the left, and we print 4. We're done with the 4. We go back up here, and we see its right side because for the 2, we've already processed it. We've already processed its left, and now we need to process its right side. So we processed a 5. We are going to print that. We return back. We return back. Okay, the 1 here, well, it's already processed itself. It's already processed its left. Now it needs to go over to the right side. So we process the 3 because that's the first thing we do. And then we process the left side. So then we go over here and we visit the 10. Okay, we are going to process the 10. That left and right quickly finish. We return back up. The 3 needs to process its right. Nothing there. And we would ultimately return back up, and that would be our list. So that's what you'd get for a pre-order traversal. Okay, now let's do an in-order traversal. So the first thing you would do is actually process your left side before you process yourself. And then you would process yourself after you're back from that left traversal. And then after you've processed yourself, then you process the right side. Okay, so let's see what that means. Well, we'd still start at the root. We still have to start at it. But by node here, we mean process the node. So even though we're kind of visiting it here, we're not processing it yet. We're not printing it
It's
it
just
yet.
like-
So the first thing we have to do is go left. Okay, we go left, which is here. Now we have to follow the same rules here because we're at a new node here. The first thing we have to do is go left. Okay.
This is just like basically breadth first search.
Okay,
What the fuck?
we go left. Same
wanna
rules.
ch-
The
oh,
first thing we have
wanna
to do is
punch
go
people.
left,
Fuck.
but there's nothing there. Okay, we're back from our left traversal, and then we process the current node. So the first thing we actually process in this in-order traversal is going to be 4. So the bottom left thing, that's what you're going to hit first in an in-order traversal. Okay, now we've processed the 4 itself. We need to process its right side, but there's nothing there. We come back from that, and this 2, it's already processed its left side, but now we need to process it. So then the second thing we're going to see, 2, there's nothing there. Process the right side. Okay, so let's see what that means. Well, we'd still start at the root. We still have to start at it, but by node here, we mean process the node. So even though we're kind of visiting it here, we're not processing it yet. We're not printing it yet. So the first thing we have to do is go left. Okay, we go left, which is here. Now we have to follow the same rules here because we're at a new node here. The first thing we have to do is go left. Okay, we go left. Same rules. The first thing we have to do is go left, but there's nothing there. Okay, we're back from our left traversal, and then we process the current node. So the first thing we actually process in this in-order traversal is going to be 4. So the bottom left thing, that's what you're going to hit first in an in-order traversal. Okay, now we've processed the 4 itself. We need to process its right side, but there's nothing there. We come back from that, and this 2, it's already processed its left side, but now we need to process it. So then the second thing we're going to see is the 2. Okay, then we need to go on its right, so we go and see the 5. Okay, its left has nothing, and then we process itself, which is going to be 5. Its right has nothing. We come back up. We come back up. Now the 1 says that, okay, we've processed its left. We're ready to process the current node, which is the 1. And so now we actually process the 1. Even though it's the first thing we visited, we still started here. We only processed it, aka printed it at this point. Okay, so now we've processed the current node. We then need to go right. So we do that for this guy here. Before we process it, we need to go left. So we are going to go left over here. Okay, now we can process the 10. We return back here. Okay, the 3 has done its left. Now it's ready to process itself. So we process the 3 itself. We do the right, which is nothing there. We return back. And then finally here for this 1, we've done all of its left, itself, and its right. So that has done the traversal. So this is what we would get in an in-order traversal. Okay, now let's do a post-order traversal. So what that means is the first thing you do is go left, and the second thing that you do is go right. And then after you've processed your left and your right side, then what you're going to do is yourself, your current node. So what that's going to be is you visit 1, but we go left. We visit 2, but we go left. We visit 4, we're ready to process itself. So again, the first thing you're going to see here is the 4. And this 2 says, okay, we've been left, but before we process ourselves, we need to go right. So we are going to see the right side, and then we see that we can process the 5. Okay, after we've done that, we return back to this 2. And he says, okay, he's processed his left and his right side. So now he's ready to process himself. So we are ready to process 2. Okay, we return back up to the 1 here. Before he processes himself, he has to go right. We have to go right. So we go over here. We're at a new node. And so the first thing we have to do is actually go left. We go left and see this one. He can process himself. We return back up here. The 3 has to go right, but there's nothing there. He sees himself. We would process that current node 3. And then we would return back up to here. The 1 would say, okay, we've done all the stuff in the left. We've done all of the stuff in the right. We're ready to process ourselves. And so, okay, we'll finish that off with a 1. So in a post-order traversal, it's post because your self comes last. We're doing it post the other stuff. So that's why, since the root let's talk about an important data structure known as binary trees. So let me draw a binary tree. It might look something like this, where we have different nodes here. And so a node is just like a circle with a value in it. We're drawing numbers in them, but they could store pretty much anything that you want. For any node that's in the tree,
டேட்டா ஸ்ட்ரக்சர்ஸ் அண்ட் அல்காரிதம்ஸ் தேவையே இல்லை அப்படின்னு யாராவது சொன்னால் தயவு செஞ்சு நம்பாதீங்க. கம்ப்யூட்டர் சயின்ஸ்னு எடுத்துக்கிட்டாலே டேட்டா ஸ்ட்ரக்சர்ஸ் அண்ட் அல்காரிதம்ஸ் அப்படின்றது ரொம்ப முக்கியம் அப்படின்னு எல்லாருக்குமே தெரியும். இந்த டேட்டா ஸ்ட்ரக்சர்ஸ் அண்ட் அல்காரிதம்ஸை நான் படிக்க போகிறேன் அப்படின்னு நீங்கள் முடிவு எடுத்துட்டீங்க அப்படின்னா அதுக்கு முன்னாடி நான் கேட்க போகிற 2 கொஸ்டினுக்கு உங்ககிட்ட ஆன்சர் இருக்கான்னு ஃபர்ஸ்ட் பாருங்க. அதுக்கு முன்னாடி இந்த மாதிரி ப்ரோக்ராமிங் ரிலேட்டடான வீடியோஸை மிஸ் பண்ணாமல் பார்க்கறதுக்கு எரர்மிக்ஸ்ல வர ஃபாலோ பண்ணிக்கோங்க. ஃபர்ஸ்ட், எந்த ப்ரோக்ராமிங் லாங்குவேஜில் நீங்கள் ஸ்ட்ராங்? நான் எந்த ப்ரோக்ராமிங் லாங்குவேஜ்லையுமே ஸ்ட்ராங் இல்லை அப்படின்னு சொன்னீங்க அப்படின்னா ஃபர்ஸ்ட் ஒரு ப்ரோக்ராமிங் லாங்குவேஜ் எடுத்து அதில் ஸ்ட்ராங் ஆகுங்க. செகண்ட் கொஸ்டின், ஹேக்கர் ரேங்க் இல்லை லீட் கோட் இந்த மாதிரியான பிளாட்ஃபார்ம்ஸில் அட்லீஸ்ட் ஒரு 50 கொஸ்டினாவது சால்வ் பண்ணியிருக்கீங்களா? இல்லை நான் சால்வ் பண்ணதே இல்லை அப்படின்னு சொன்னீங்க அப்படின்னா ஃபர்ஸ்ட் அதை போய் சால்வ் பண்ணுங்க. இது ரெண்டையும் பண்ணதுக்கு அப்புறமா டேட்டா ஸ்ட்ரக்சர்ஸ் அல்காரிதம்ஸ் போங்க. இல்லைனா ரொம்ப கஷ்டமாக ஃபீல் பண்ணுவீங்க. பாதியிலே
நீங்கள் வந்து டெவலப்பராக இருந்ததால நீங்கள் கோட் மட்டும் பண்ணி கொடுத்துட்றீங்க. அதுக்கப்புறம் என்ன நடக்குதுன்னு உங்களுக்கு தெரியல. பட் அந்த டைம்லேயே டெவாப்ஸ் இன்ஜினியர்ஸ்னு இருந்தாங்களா?
அப்போ வந்து கிளவுடுக்குள்ளலாம் யூஸ் பண்ணல. AWS cloud எதுவுமே இல்லை. ஒரு ரேக் சர்வர் இருக்கும் சார். நீங்கள் இன்னும் ஞாபகம் இருக்கு, லைக் ஒரு 3rd floor போனால் ஒரு சர்வர் வச்சிருப்பாங்க. அந்த சர்வருக்குள்ளே போயிட்டு அவர் போய் ஏதோ டிப்ளாய் பண்ணுவார்.
ஃபர்ஸ்ட் டெவாப்ஸ் தேவைப்படல, இப்போ டெவாப்ஸ் தேவைப்படுது. அந்த எவல்யூஷன் எப்படி இருந்துச்சு? எந்தெந்த ஸ்டேஜில் டெவாப்ஸ் வந்து தேவைன்னு சொல்லி கண்டுபிடிக்க ஆரம்பிக்கிறாங்க?
ஒரு 3 hours இன்ஸ்டாகிராம் யூஸ் பண்ண முடியாது அப்படின்னு சொன்னால் ஒத்துக்க மாட்டாங்க.
1 minute இன்ஸ்டாகிராம் டவுன் ஆனாலே ஃபுல்லாக எல்லாரும் பிளாஸ்ட் ஆயிடுறாங்க. இன்ஸ்டாகிராம் ஒர்க் ஆகல.
நம்ம நைட் 2 o'clock கூட சொல்ல முடியாது. 2 o'clock யூஎஸ்ல யாராவது யூஸ் பண்ணிருப்பாங்க. ஸோ அப்படி பார்த்தீங்கன்னா லைக் 24 hours ஆகணும் அந்த அப்ளிகேஷன் அப்பா இருக்கணுன்றது வந்து நம்ம மைண்டில் ஒரு பேசிக் நீட் மாதிரி ஆயிடுச்சு.
கோட் பண்ணி முடிச்சுட்டு சென்ட் பண்ணுறாங்க. பட் கோட்டர்ஸ் என்ன நினைப்பாங்க அப்படின்னா என்னோட வேலை முடிஞ்சுன்னு சொல்லி நினைப்பாங்க. பட் அங்கே டெப்ளாய் பண்ணுறப்ப இன்டர்நெட்டில் எல்லாரும் பார்க்கணும், லைவ் பண்ணணும்னு நினைக்கிறப்ப அங்கே ஒரு எரர் வருது. திரும்ப ஏன் எரர் வருதுன்னு இன்னொருத்தர் பார்த்து கேள்வி கேட்குறாங்க. அதை அப்ரூவ் பண்ணி திரும்ப கோடர்ஸ் கிட்ட வருது. கோடர்ஸ் திரும்ப எதனால பிரச்சனைன்னு சொல்லி ஃபைன் பண்ணுவோம்.
மவுண்டைன் வந்து ரொம்ப சின்னதாக இருக்குது, ஆனால் ஹவுஸ் வந்து ரொம்ப பெருசாக இருக்குது. அது எனக்கு எப்போ தெரியுது? மவுண்டைன் சின்னதாக ஹவுஸ் ரெண்டுமே வைக்கும் போது தான் எனக்கு தெரியுது. அப்புறம் என்ன சொல்கிறேன், இல்லைங்க இது தப்பாக இருக்குது, இது மவுண்டைன் வந்து பெருசாக இருக்கணும், வீடு எப்பவுமே சின்னதாக இருக்கணும், நீங்கள் திரும்ப பண்ணி கொடுங்க அப்படின்னு சொல்கிறேன். ஒரு டெவலப்பர் வந்து டாஸ்க் கொடுத்துரும், இந்த ஃபங்க்ஷனாலிட்டி பண்ணுன்னு சொல்லிட்டு அதை முடிச்சிட்டேன் அப்படின்னு சொல்லிட்டு அடுத்த ஃபங்க்ஷனாலிட்டி போயிட்டாரு. ஆனால் ஃபங்க்ஷனாலிட்டி 1ல பிரச்சனை வருது. இப்போ என்ன பிரச்சனை ஆகும்? அந்த ஃபங்க்ஷனாலிட்டி 1 பண்ணுறதா 2 பண்ணுறதா? சரி 2 பண்ணி திரும்ப போடும்போது பார்த்தா 3 பண்ணிட்டு இருக்கும்போது 2 1ல பிரச்சனை வருது. சரி இந்த லூப் எல்லாமே அவாய்ட் பண்ணலாம்.
நீங்கள் டெவலப்பராகவும் இருந்திருக்கீங்க, டெவாப்ஸ் இன்ஜினியராகவும் இருந்திருக்கீங்க. இது ரெண்டுக்குள்ள டிஃபரன்ஸ் என்ன? இது ரெண்டுக்கும் வெயிட்டேஜ் கொடுக்கணும்னா எதுக்கு மோர் வெயிட்டேஜ் கொடுப்பீங்க?
டெவாப்ஸ்ல இருக்க பெரிய விஷயமே இனிஷியலா செட்டப் பண்றது ஈஸி, பட் ப்ரொடக்ஷன்ல இஷ்யூன்னு வரும்போது அதை நம்ம எப்படி சால்வ் பண்றோம்ன்றது தான் முக்கியமான சேலஞ்ச்.
ஒரு ஃப்ரெஷர் டெவாப்ஸ் இன்ஜினியர் ரோல் வர்றதுக்கும் ஆல்ரெடி ஒர்க் பண்ணிட்டு இருக்கிறவங்க டெவாப்ஸ் இன்ஜினியர் ரோல் வர்றதுக்கும் என்ன டிஃபரன்ஸ் இருக்கு?
ஃப்ரெஷர்ன்ற டாக் நான் எப்படி பண்றேன்னா அவங்க அப்ளிகேஷனே பில்ட் பண்ணது இல்லன்றதான் ஃப்ரெஷர். ஃபார் எக்ஸாம்பிள் இப்போ நீங்க காலேஜ் செகண்ட் இயர்லயே அப்ளிகேஷன் பில்ட் பண்ண ஆரம்பிச்சிட்டு இஃப் யூ ஆர் டூயிங் லைக் பார்ட் டைம் ஃப்ரீலான்சிங் அந்த மாதிரி பண்ணிட்டு 4th இயர் உங்களுக்கு ஏற்கனவே அப்ளிகேஷன் நாலேஜ் இருக்குன்னா ஐ திங்க் லைக் வில் நாட் பி டாக்ட் அஸ் ஃப்ரெஷர்னு தோணுது.
டெவாப்ஸோட ஃபண்டமெண்டல்ஸ் அவங்க தெரிஞ்சுக்கிறதுக்கு இந்த 5 விஷயம் அவங்களுக்கு தெரியணும் அப்படின்னா என்னென்ன சொல்லுவீங்க?
நுனிப்புல் மட்டும் மேஞ்சா ரொம்ப பிரச்சனை. மீனிங் லைக் நான் ஒரே வீடியோ பார்ப்பேன் அப்படியே நான் வந்து டெவாப்ஸ் இன்ஜினியர் ஆயிடுவேன்றது சான்ஸ் இல்லை.
எனக்கு கோடிங் வராது, அதனால நான் டெவாப்ஸ் சூஸ் பண்றேன். இந்த 4 டூல படிச்சா நான் டெவாப்ஸ் இன்ஜினியர் ஆயிடுவேன். இதை எப்படி பாக்குறீங்க?
கோடிங்கே வேண்டாம், நான் வந்து வெறும் ஆப்ஸ் மட்டுமே இருப்பேன்னு வச்சிங்கன்னா மேபி யூ வில் கெட் அ ஜாப் இன் லைக் 2009. பட் ஆனால் இப்போ 2025 இருக்குமான்னு பார்த்தா ஐ திங்க் இட்ஸ் வெரி வெரி டிஃபிகல்ட்.
இந்த டூல்ஸ்லாம் இவங்களுக்கு கண்டிப்பா தெரிஞ்சிருந்தா இந்த அண்டர்ஸ்டாண்டிங் வந்துடும் அப்படின்ற மாதிரினா என்ன டூல்ஸ்லாம் கண்டிப்பா அவங்க யூஸ் பண்ணணும் அப்படின்னு சொல்லி சொல்லுவீங்க? யாருக்கு டெவாப்ஸ் சூட் ஆகும், யாருக்கு டெவாப்ஸ் சூட் ஆகாது? இவ்வளோ டைம் இவ்வளோ மந்த்ஸ் நீங்கள் வந்து சாலிடாக ஸ்பெண்ட் பண்ணால் ஒரு டெவாப்ஸ் ரோல்குள்ளே போகலாம், இவ்வளோ மந்த்ஸ் ஸ்பெண்ட் பண்ணால் போகலாம் அப்படின்ற மாதிரி ஏதாவது டைம் பீரியட் இருக்கா? ரியாலிட்டி டைம் பீரியட்.
Hey guys, welcome you all to another episode of Value in the Making. Python
10-hour tutorial. Fucking dork. Dork. Are you a dork? Are you a dork? You are a dork, bro. Are you a dork? Bro, that's crazy. 2 years, 1 million. Bro, I respect the hustle. Fucking hell, I respect the hustle, bro. I mean,
Python ஒரு ப்ரோக்ராமிங் லாங்குவேஜ் அப்படின்னு.
bro, I respect the hustle. Fucking hell. I didn't even know this guy existed.
Since the root is actually the first thing that we visited, well, it's actually the last thing that we're going to process. You could also do a breadth first search, or a BFS, and so that would be a level order traversal. So particularly for trees, you might see this be called a level order traversal, because it's basically visiting the tree level by level. So you could do that. That would see 1, and then you would see 2, and then 3, and then 4, and 5, and 10. And there's none of that sort of in order, post order traversal stuff. It's really just visiting it level by level. Now, the reason that's called breadth first search, or BFS, is because we prioritize breadth. You can picture of it kind of spreading yourself thin. Depth first search, or DFS, that would prioritize depth. So basically, we're going one way here. We're going down. You could do a DFS where you visit the right side. Generally, it's on the left side, but either way, you're kind of prioritizing depth, or going down. Whereas a BFS here, a breadth first search, you're prioritizing breadth. So if you see this guy first, well, then you kind of want to spread yourself thin here. You want the next thing to do is to visit this guy, and then after that you want to visit this guy. And then since we saw the 2 first, you would want to see its neighbors. And yes, I'm using the term neighbors. That's a graph term because trees are a subclass of graphs. So the next thing we'd want to see is 4, and then 5, and then since you saw 3 earlier, you would want to see its neighbors next of 10. So depth first search prioritizes depth, and breadth first search prioritizes breadth. And it turns out that depth first search is generally implemented by using a stack, and breadth first search is generally implemented by using a queue. So DFS, we often write this as recursive, so you'd use recursion to do that, except recursion uses a call stack, which really just means it's using a stack. So DFS, whether it's recursion or quite literally using a stack, so DFS will be implemented with a stack, and BFS will be implemented with a queue. Okay, so let's see how to do a depth first search. You would use a stack, and if it's recursion, it would just be a recursive call stack. So what you would do is you would make an empty stack, and you would initialize it with just the root node on the stack here. So I'm drawing it with this circle in it to imply that we're actually putting the node itself and not just the node value of 1 on the stack. Okay, so you initialize it like that, and then basically you would do this. You'd say while you have a stack, which basically just means while the stack is not empty, you're going to pop an element from the stack. So what we do is we pop this, and that's when we process it. So we're going to pop that, say, okay, we've seen the 1, and we're currently processing the node of 1. Okay, then what you would do is you'd say, okay, do we have a right node? Yes, we do. Since we do, we're going to put that on the stack. Do we have a left node? Yes, we do. Okay, we're
I kind of get the point. I get the point here.
If you've been trying to learn to code or break into tech for more than just the last couple of years, you're probably familiar with the term tutorial hell. Everyone was stuck in tutorial hell. Really was. Videos have a place in types of they're not even really building the things. They're fighting hallucinations. They're going to war with an optimistic, I see the problem now, sycophantic models. They're doing sweet battle with bots that are more interested in getting their newly generated test suite to pass than actually solving the user's problem in a simple way. And as we all know, vibe coding tends to be easiest at the beginning of a project. Once the code base begins to grow and you don't understand the underlying architecture, you don't understand how to deploy it, right? You're stuck on localhost, you don't know how your system actually works. That's when these things really start to slow down. And that's when you want to go back and understand how your code actually works, but now the code base is too massive. And as we all know, reading code, especially reading someone else's code, is usually even harder than just writing the code ourselves. Now, I don't want to make this whole video about when or if AI is replacing developers. I don't think it is in the near term. We're 3 years into 6 months until AI takes your job, and I'm still here and I'm still hiring developers, so not too worried about it. And GPT-5 just dropped, and it was an incremental improvement over GPT-4 for sure. We immediately updated boots to use it on boot dev, but to me, it honestly feels like a smoking gun that AGI is not coming anytime soon. If GPT-5 was AGI being achieved internally, I don't even know what AGI means. And look, I use AI tools every day. Occasionally I find a well-scoped task that I can offload to an agent. I use chatbots to double check some of my work and bounce ideas around, but frankly, I'm still unsure how much more productive AI is actually making me. Sometimes I think it's just letting spend of 1.5. What's my true return on ad spend? ChatGPT said it's ROAS of 1.5. What's my... Don't go to experts to have them agree with us. We go to experts because we want them to point out the flaws in our logic. That's why experts are valuable in the industry. We ask experts so they can tell us when we're wrong. IRC chats and Stack Overflow were honestly probably too good at this. Now students just have cozy chats with LLMs instead that tell them what they want to hear, tell them how smart they are, but not what they need to hear.
Yeah, that's true.